Hello everyone, my name is Denis Antipov, I'm from ITMO University, and my talk will be about the lazy parameter tuning and control, which is a joint work with Maxim Buzdalov from ITMO University and Benjamin Doerr from École Polytechnique. So, the parameters are important in many spheres. For example, imagine that you have a race car and it has many different things you can to adjust, like the brake balance, or you can choose different tires. And when you face some track, you want to choose these parameters in the way so that your car was the fastest on this track. But it's always a non-trivial question on how to set these parameters for the best performance. But in the evolutionary algorithms, this approach is named as static parameters choice, but there is also an opportunity to choose parameters in every iteration of the evolutionary algorithm. So there is another question on how to choose the strategy of choosing the parameters, which is usually called the dynamic parameter choice. So both these approaches have the pros and cons, and for example, theory suggests that they can be both can be beneficial in some situations. And for example, for the 1 plus lambda, lambda GA on ONEMAX problem, it was shown that the best runtime we can obtain with the static parameters is for the n multiplied by the square root of logarithm of n, but choosing lambda dynamically, we can obtain a linear runtime, and we can do it in different ways actually. On the other hand, for the 1 plus 1a on jump k function, we can choose the right mutation rate, which is k over n, and then we can obtain this runtime. But if we miss this right mutation rate k by a constant factor, then we have this additional factor to the runtime. So, and but here we have a problem that we need to know this parameter k of the function to choose the right mutation rate. And actually the dynamic parameter choice can let us have a runtime which slightly worse than this one, but for any value of k. So the additional factor is much less than this exponential factor. The story becomes even more interesting when we have more than one parameter, and previously in most theoretical works only one parameter was chosen or controlled dynamically, and other parameters were set up according to this one. In our previous PPSN paper, we considered the 1 plus lambda, lambda j, where we select two different parameters independently, but then we have a third parameter which we set up equal to the to one of the these chosen dynamically. So there is a dependency which is very problem specific. And in this work, we propose to choose all three parameters of the 1 plus lambda, lambda j randomly and independently from each other, and we show that this simple approach can give us a very good performance both on easy and on hard functions. So we propose to choose these parameters from the power law distribution. This is such a distribution that where we choose a random variable from the interval from 1 to u, where u is the upper bound, it is a parameter of the distribution. And the probability to choose the random variable equals to I is proportional to I in minus beta, where beta is the parameter of the distribution, and it's called the exponent of the power law distribution. So here you can see an example of the PMF for a very large u, and beta equals to 2. And the main features of this distribution is that if we choose beta greater than 1, which is the most interesting for the practical use parameter value of the exponent, then we have a constant probability to choose small x, so not greater than a constant, but at the same time we have a very good probability to choose x large. So for example, if there is an interesting interval from a to 2a for the choice of x, then the probability to choose x from this interval is a into 1 minus beta. And if beta close to 1, this is quite a good probability. And also, if beta is greater than 2, then the expected value of the runtime variable is constant, which means that it might be beneficial when we choose parameters like the population size, which affects the cost of one iteration. So we adopted this strategy of choosing the parameters in the 1 plus lambda, lambda j. So this is a genetic algorithm for the pseudo-Boolean optimization, which has 3 parameters: mutation rate p, crossover bias c, and population size lambda. It has only one individual, which is initialized with with some random bit string, and then it performs iterations, which consist of the mutation and crossover phases. In the mutation phase, we create lambda offspring by flipping the same number of bits in them in X, and this number is chosen from the binomial distribution with parameters n and p. So this is something like performing a standard bit mutation with mutation rate p, but conditional that all offspring must have the same distance from their parent. And then we choose the best of them as the mutation winner x dash. In the crossover phase, we take x and x dash and apply a biased crossover to them and create another lambda individuals. And this biased crossover takes each bit with probability c from x dash and with probability 1 minus c from x. Then the best offspring from the crossover phase is compared to the current individual x, and if this crossover individual is not worse, then it replaces the current individual. Well, so here we propose to choose all the parameters of the algorithm in the start of each iteration. So we choose p, c, and lambda from some power law distributions. And here are our suggestions for the meta parameters of the algorithm, which are the parameters of the distribution which we use for the choice of the parameters. So for p and c, we suggest to use the distributions with beta which is slightly greater than 1, and with upper bound which is square root of n. Since p and c must be in interval from 0 to 1, these are 2 probabilities, we also normalize this power law distribution, but this 1 over square root of n factor. So these meta parameters give us the following features. So on the one hand, we can choose very small p and c, so that pc equals to 1 over n, and this product of p and c for the 1 plus lambda, lambda j is something like the mutation rate for the 1 plus 1a, and there is a common recommendation to use this mutation rate equals to 1 over n. So on the other hand, we also very likely to choose them large if we need this on our problem. The normalization itself, together with this upper bound, is actually an open question how to better choose it, but it seems like this square root of n upper bound and this normalization factor work quite well both on easy problems and also on hard problems like jump. So for the for the choice of lambda, we propose to choose the exponent which is slightly greater than 2, because in this case we will have a constant cost of one iteration. It actually doesn't really matter which upper bound we choose for these values of beta, but for small values of beta, 2 into the power of n might be a good upper bound. And also, this guarantees that we still have a heavy tail distribution, which means that we have a very good probability to choose large values of lambda. Okay, we performed an analysis on some easy problems, and this analysis is based on the observation that our heavy-tailed 1 plus lambda, lambda j makes an iteration which is equal to an iteration of the 1 plus 1a with constant probability, which means that it chooses lambda equals to 1 and p equals to c equals to 1 over square root of n. All this happens with a constant probability, and then it means that we create only one mutation offspring and then only one crossover offspring, and in this offspring each bit is flipped with probability 1 over n. So it's generally the 1 plus 1a with the standard bit notation. So the corollary is that the runtime of the heavy-tailed 1 plus lambda, lambda j is the same as the one of the 1 plus 1a if this runtime was proven via the fitness levels technique or via the drift analysis. So, for example, we have a quadratic runtime on leading ones problem, we have this runtime on the MST problem, and we have a linear runtime on the approximation of the partition problem. So, for the hard function, we chose the jump function. So, this is generally the ONEMAX function, where we count the number of 1 bits in the bit string, but when this number of 1 bits is close to the optimum, so it's in the in radius k of the optimum of ONEMAX, we have this fitness value of extremely low fitness. So, and the analysis on this function showed that we have a very good probability to choose P and C in this interval, which was shown to be close to the optimal values in our last year paper. And then we compute the probability to find the optimum in one iteration, which we where we use the law of total probability over all possible choices of lambda. And one can say that approximately after we reach the local optimum, which we reach in very short time because of our analysis, as our analysis on easy problems shows us. So the runtime actually follows the geometric distribution with parameter p. So it means that its expected value is 1 over p. And then we can also compute the expected number of fitness evaluations, which by Volt's equation, and since the expected cost of one iteration is constant, is of the same order. So we here we show the probability to choose the good values of P and C, which is the best for beta P and beta C, both greater than 1. Mostly because it doesn't depend on the upper bounds for the distributions for P and C. But also we can notice that the total runtime is the best when beta lambda is in the interval from 2 to 3, and you can see that this runtime is this one, so it's e into something like into power of, roughly speaking, k, and multiplied by n over k, in the power of k over in the power slightly greater than k over 2. So this upper bound on the runtime doesn't depend on our choice on the upper bound of for lambda, and it also hides this PC factor, so the probably choose these parameters here in this exponential factor. So to compare this with static parameters, we can see that if we choose the right static parameters, and if we start from the local optimum already, and then the runtime is slightly better. But if we have to choose to also take into account the time until we reach the local optimum from some random bit string, then we need to choose other different parameters, because these parameters are very ineffective in the easier stage of the jump function. We get this runtime for the best static parameters, and you can see that for constant k and some small epsilon, here it can be we can actually obtain a better runtime using the dynamic parameters. So, which is a clear advantage of the dynamic parameter choices. So, we also performed some experiments to find the precise best values for the meta parameters of the algorithm, because all our theoretical results are just asymptotical. So, for this we considered ONEMAX and jump problems, and in all our experiments we set up the same beta P and beta C, not to deal with too many meta parameters. And we performed 100 runs for each parameter setting. So first we fixed beta lambda and ran the algorithm with different values of beta PC. and compared it with the 1 plus 1a. So you can see that the larger values of beta PC work better. Well, so it means that the better concentrated PNC fit us better on ONEMAX. And also we can see that we don't outperform the 1 plus 1a, but we only lose it something like a factor of 1.7, which is very small loss. Well, it was also interesting which value of beta lambda is the best, so we fixed the problem size and performed the experiments and saw that, well, maybe it's better to recommend beta lambda equals to 2.4. And we also can see that this trend from the previous plot, where we see that this greater beta PC, the better the runtime is, also saves for all values of beta lambda. So we also were interested in the experiments when we start close to the optimum, and we run our algorithm starting in distance square root of n from the global optimum, and we can see that the 1 plus lambda comma lambda j has sub n log n runtime in this setting. So on jump problem we couldn't run too many experiments due to the large runtimes. So but here you can see that for the parameters we for the meta parameters we observed here, the heavy-tailed 1 plus lambda comma lambda j was much better than the 1 plus 1a. But actually the precise choice of these meta parameters wasn't very important. So we also were interested in the best values for beta lambda, and we can see that the smaller beta lambda is the better the runtime, and it can be explained that the smaller beta lambda actually gives us a better chance to choose large values of lambda, which is very beneficial on the jump function. So to sum up this talk, we have shown that the heavy-tailed parameter choices can be effective on different kinds of problems, like on easy and hard problems, even when we have to choose more than one parameters and independently from each other. And from experiments we saw that the precise choice of these meta parameters of the Pavlov distributions, which we use for the choice of parameters, doesn't play much role. And but there is still an open question on how to choose the right scaling for some parameters, like for mutation rate and crossover bias. But we assume that even if we miss the right scaling, we still don't pay much for this. So it is quite an algorithm which works out from the box. So that's all. Thank you for your attention.